Okay, good afternoon, everyone. I'm Professor Liu, so I will be responsible for this subject, engineering thermodynamics, for this semester. So as we know, we have three fundamental subjects for our BS degree and also structural fire engineering. So as we know, we have fluid mechanics. I think last we have learned this subject in our last semester, and also for this semester we have heat transfer. And together with engineering thermodynamics, these three are the fundamental subjects. Today, we will introduce engineering thermodynamics, and we will learn how to apply the first law and the second law of engineering thermodynamics, and to find out the solution to convert heat to work or convert work into cooling or heat. So why heat engines? Firstly, I would like to introduce myself. Okay, I think I'm new for you. So in fact, I'm a full professor of the Department of Building Services Engineering Department. And my office, so it's my office is ZS850. This is my phone number, and this is my email address. Sure, if you have interest, you can find more information, my personal information, my research interests from website. So besides my expertise in building sciences and engineering, in fact, I'm also expertise in renewable energy and renewable energy technologies in green buildings. Sure, recently I'm also working on some multidisciplinary research area like green building nanomaterial development. So here is a video showing my exposure to offshore wind farm. So one of my research interests is on wind power utilization. Okay. Okay, cannot click. Okay, then I show you the other. So that's me. That's me. I'm working on solar energy and wind power utilization. Sure, I'm working in the field of building sciences and engineering. So for today, in fact, we will have a brief introduction to engineering thermodynamics and its correlations to HVACR and also combustion. And sure, today I will also, we will together have a quick look at our teaching scheme and the assessment. And sure, so today later, we will start our lecture on the fundamentals of engineering thermodynamics. So according to the definitions, we can see thermodynamics. So for thermal, it means heat energy, dynamics, which means conversion or transformation. So therefore, in fact, thermodynamics is the science to understand energy in all its forms, such as mechanical, electrical, chemical, and how energy changes forms. So we can say we will understand energy in different forms and the energy transformation or energy conversions from one form to the other. Applied thermodynamics is the science to formulate and uplift the theories of applied our thermodynamics, and to understand the relationship between heat, work, and the properties of a system. So it's very interesting. In fact, for this subject, we merely understand the relationship between heat and work, because we will find, so we will, for our first tutorial, they will be, it will be in-class quiz. Then I will try, I would like you to find out some examples. So the relationship between heat and work, how there is energy conversion from heat to work or work to heat, and also how to achieve the energy transformation between heat and work. So usually there's undergo the property changes of working fluid in the system. So therefore, in fact, we have three focuses. We have to understand the relationship between heat, work, and also we have to understand the properties of a system, so the properties of working fluid in a system. So, and it is also help us to understand how to convert heat energy from other sources, such as fossil fuel, into mechanical work, etc. Then we understand for applied thermodynamics is to try to understand the relationship between heat and work. So how they transforms from one form to the other. So according to the definition, we understand work is the form of energy useful in displacement of a body. Displacement. So according to the definition formula, we know the work, in fact, is the force, and the displacement in the direction of the force. Okay, then we can calculate work. So sure, so we have we will you can see a baseball pitcher. They does positive work on the ball because there is displacement or movement of the ball. So it's giving it a force, and also in the direction of the force, it moves. And then this is work. Then what about heat? In fact, heat is the form of energy transferred due to temperature gradient. So we have at the beginning, we have mentioned the heat transfer. So heat transfer is heat transferred. It's due to temperature gradients. Whenever between any two bodies with temperature gradient, so there is a heat transfer. So heat transfer can be in the form of conduction, convection, or radiation. So for example, we see a red hot iron rod. So why you feel hot? That's because between you and the hot rod, there is radiation heat transfer. Although we don't touch it, but there is radiation heat transfer between you and the red hot iron rod. Also, like when there is a fire in front of you, you also feel hot. That's because between you and and the fire, there is radiation heat transfer. So now we understand what is work and what is heat. In fact, for engineering thermodynamics, we try to understand the relationship between work and heat. Later, we will understand there is energy conservation, so according to first law of thermodynamics. However, work can be converted to heat, but if we want to convert heat into work, we need heat engines. So it cannot happen naturally. So we need heat engines. And for the application of engineering thermodynamics, in fact, that's mainly to design various systems by using fluid properties to cause energy transformation. So, for example, this this is for power plants. For power plants, in fact, there's a combustion of fossil fuels. So from chemical energy into thermal energy. Then the thermal energy by using heat engines. So it can the thermal energy can be transformed into rotational mechanical work, the rotation of the turbine. Then it's connected to power generator. It can produce electricity. Okay. And also, later we also will know if for air conditioning, for our home refrigerator and air conditioner, so we have the other types of heat engines. So for this subject, we will mainly introduce the fundamentals of engineering thermodynamics and to understand the fluid properties in the system, and also by using the changes of the fluid properties to achieve energy transformation, like this example, from thermal energy into power, into work, and then finally into electricity. And also we have the heat engines, like our home refrigerator, air conditioner. So by the changing of the fluid properties in the heat engines to provide cooling or refrigeration. So don't worry at the moment because very soon later we will introduce all this in details. So I think I still want to share some with you, so what's the relationship between engineering thermodynamics and our building services system, especially heating, ventilation, air conditioning, refrigeration, and combustion. And for heating, in fact, it's the process of maintaining temperature at an acceptable level of using thermal energy within a house. So the heating can be achieved. So usually, we can see there is a combustion turbine to produce hot water or steam. The hot water and the steam will carry the thermal energy, the heat, and circulate it into the building to heat the space. And for ventilation, for V is ventilation. Ventilation is the process of changing or replacing air in any space to control temperature or remove any combustion or moisture, odor, smoke, heat, dust, etc. So we can say usually like our car park, we have mechanical ventilation. We want to remove the carbon monoxide produced and the vehicle emissions, okay, from the car vehicles. We need to remove or dilute the harmful particles and some harmful gases. And also, like our toilets, we need ventilation system to remove the odor. And also, for example, if there is a fire, we need a smoke extraction system, okay, to extract smoke and heat, okay, of a fire, to provide safe escape route for the occupants. Sure, for ventilation, we have mechanical ventilation. So for mechanical ventilation, we have to use the design fan, okay, ductwork system to remove the contaminated air. And nowadays we talk about natural ventilation. Then we try to use the natural resources like natural ventilation to remove the contaminated air by replacing outdoor fresh air. For refrigeration, so generally we understand like there is a commercial refrigerator like our home refrigerator. So we think it's strange because it can provide cooling. However, it's not for free. So it has to reject heat. Although it provides cooling and refrigeration like our home air conditioner. But when we walk near the outdoor units of air conditioner and also our home refrigerator, you will feel there's heat waves. Okay, there's heat rejection from the air conditioner. Okay, so we found that in fact we remove the heat, provide cooling and refrigeration. However, we need electricity power input, and we also will reject heat into our ambient air. So we all have to consider, for example, like this home air conditioner, you can see here to provide cooling. However, outdoor units, we have to reject the heat into our ambient air. That's because the first law of thermodynamics. And for air conditioning, in fact, is the process of treating air in an internal environment to establish and maintain required standards of temperature, humidity, cleanliness, and air motion. Okay, so not only for temperature control, but also for humidity control. And also we have to design air distribution system to, and also we need to we have to select the filters to ensure the cleanliness of the space, and also to control for air distribution system to provide air motion to avoid stagnant air. And sure, so we can see we have the combustion engines. So combustion engines everywhere, even so we can see for a combustion. So in fact, is the chemical reaction of combustion is to there is energy confirmation of the chemical energy stored in the fossil fuels or the fuels, okay, to heat. And the combustion engines can be applied in many industry areas. For example, so for the vehicles, for our cars, there is combustion engines. So there is a combustion. So we can see there is a fuel injector. So there is combustion of the fuel. Therefore, there's air movement to push the piston movement. Okay, finally to drive the vehicle wheels. Okay, and sure, we also have combustion engines for our power plant. Okay, for our power plant. So we feed feed in the fossil fuels combustion, then to generate high temperature, high pressure steam to drive the rotation of the turbines to produce work or electricity. So for air conditioning system, it's simply we have different loops. So we can see for air conditioning system, we want to provide a cooling for the air conditioned space. And in fact, we will reject heat to our environment. And we have this is a refrigeration cycle. Okay, refrigeration cycle, we will learn this is a heat engine. It's not for free because we have to, there's energy use or energy consumption to achieve the air conditioning. For the teaching arrangement of this subject, so we still keep it the same. So the coursework and examination. And we have 2 1 hour not closed book, just online, okay, online tests. And we have lab reports. We have to conduct do 2 lab experiments, and also sometimes we have assignments. They will account to 5% of final assessment. And all of you have to do the 2 laboratory experiments. So one is to investigate the characteristics of a compressor of a reverse heat engine, and also to investigate how to improve the refrigeration performance by superheat. I just checked our blackboard. We have the arrangement for our laboratories. So you have the video. We have the video shooting clip already, and also you can choose to come back for face-to-face experimental work. Okay, I remember it's before February 7. You can choose if you want to come back to conduct the experiments by yourself. So this is the one for refrigeration system, superheat.
For the investigation of refrigerant system superheat, let's first look at the classic refrigeration cycle. It comprises of 4 processes which take place in the compressor, condenser, expansion valve, and evaporator. And in this experiment, we are going to investigate the influence of superheat, which is the superheat degree that the refrigerant enters the compressor.
To be honest, I think it's at the moment is still challenging for you to conduct this experiment, because we will introduce, I think, refrigeration in week 9, around week 9. Then, if for the students, you will first conduct the experiments before it. Maybe you need to study, do a good preparation. So for this experiment. So for the second one, is the same to investigate the performance of refrigeration
This is experiment A11, investigation of the characteristics of a refrigeration compressor. After watching this video, you should be able to understand the changes in the mechanical and volumetric efficiencies of a refrigeration compressor operating under different compressor loads and compression pressure ratios. The equipment we are going to use for this experiment is the refrigeration laboratory unit manufactured by PA Hilton Limited. It consists of a twin-cylinder compressor driven by an AC motor, a water-cooled refrigerant condenser, a thermostatically controlled expansion valve, and lastly, an evaporator. The unit is also equipped with...
Okay, I think someone typed a message to me. I will have a look. Okay, so for the experiments, you can see, I think you can conduct online, or you can choose face-to-face. But you need, yeah, you can choose by yourself. So you go to the laboratory. Maybe I share the. Let me have a look. Okay. I think we have anyway. You go back to our for the there is a folder. There is for the laboratory. Let me see. Okay, I will share. Let's have a look at. Okay, so let's have a look. In fact, we have the courses of BE2 laboratory. Okay, if you enter, okay, you will find. We will find. Okay, we're getting started. We have so here are the arrangements for our two laboratory. So here, in fact, you can see there is one option, registration for face-to-face lab session, but you need to fill in the form on or before 7 February. Okay, I think we still have more than 2 weeks for you to choose if you want to come back to conduct the experiments by yourself. Sure, if you cannot make it, you can also. So we also have we have also uploaded the videos, okay, to show you. So so how to what's the procedure to conduct this experiment. If you have any further questions, maybe we can discuss during our break. And so that's for the experiment laboratory work. Then come to the arrangement of this subject. In fact, be careful, because here we can see the first tutorial session is there's no class. So in the coming, this is group 2, this is group 1. And for this Thursday, in fact, we will have 15 minutes in-class quiz. Okay, in-class quiz. I have created the folder, so you need so for this for the tutorial, so we will have an in-class quiz. You have to upload your answer, okay, through the Blackboard. So we have lectures, okay, and the tutorials. We will have a Chinese New Year break, and very okay. I think some of you have questions. Then I will not go back. Because here from this screen I cannot see the messages. This is not good. Okay, we will come back later. So during break I will answer your question. So most importantly, so for week 8 we will have our first in-class test. Okay, so the first in-class test will cover what we have learned before that week. And then after in-class test 1, we have our lectures. And then we have our lecture 11 and also our revision later. If you get any question, I'm not sure because at the moment our online mode, I'm not sure if later we will change to face-to-face. I'm not sure. I will update our teaching scheme if there is any change. Sure. I would also like to share with you that all of you have known that, in fact, since last academic semester, we have a new grading system. Okay, so for your subject, you will have grades. In fact, with A plus, A minus, etc. And look at here. In fact, for academic probation, in fact, it's lowered from 2 before to 1.7. And even for your progression and graduation, so for your honors, so the award classification, the honors degree, so we can see you are very lucky. The award GPA range, so for first class honor, so before from 3.7 to 3.6. And also for the if you can pass, then for the pass before is 2. Okay, the award GPA is about 2. Now it's about 1.7. So this is our new grading system and new award GPA ranges for award classification, which both are different from old grading and award classification system. And now we will start our. So for the teaching scheme, maybe I come back to have a look if you have any questions on the teaching arrangement and laboratory work. Okay, let me have a look at your question. Okay, some of you are curious about the in-class quiz. Yeah, I think the in-class quiz contribute to 1%. Okay, 1%. Because it's only so for assignments. So for the assessment, we can see. So there's only 1%. Okay, 1%. 1%. Maybe I'll come back using here. Okay, come here again. So for the in-class quiz, because before I planned we have a recap and a mini workshop, I want all of you can be involved to present. However, this year I found out the size of our class is too big for the, I just received the name list of our subjects is totally, I think, around 60 students. We have totally around 60 students, so it's difficult for me to arrange the mini workshop. So then I decided to change it in-class quiz. So for this in-class quiz, that's what we have learned. Yeah, in fact, mainly today. However, it's open. Okay, it's open. Any solutions? In fact. Although it's I will for your grading, maybe I will only give you a pass or fail. Okay, so if you don't worry about the in-class quiz. So for in-class quiz are mainly designed because it's for fairness. We have 2 tutorial sessions. So then for fairness, in fact, the in-class quiz, I will only, we have only pass and fail, okay? If you pass. Okay, sure. I think all of you will pass it. So for fairness, because I found it's difficult, we have 2 tutorial groups, okay? Don't worry, also you don't need to prepare for the in-class quiz, okay? Or in fact, you can find solutions from our lecture or from internet. Okay, the other question. Your quiz is scheduled, is tutorial, okay? So this is a tutorial time. Tutorial time. I have created the folder. So for the in-class quiz, around 50 minutes, you need to submit your answer sheets, okay? Answer scripts. So via Blackboard. You don't need to prepare for the in-class quiz, okay? I only want to broaden your knowledge. So for this subject, and you will find this subject is very useful for us to observe and to observe the phenomenon and our universe. If no, so for the in-class quiz, the in-class quiz is in-class quiz. You need to submit your answer scripts during the tutorial session. Okay, during the tutorial session. Okay, we can discuss more about the arrangement of in-class quiz. You don't need to prepare for it, so take it easy. I only want you to broaden your understanding and find out is very interesting for this subject. Okay, now let's start our lecture on this subject. Is the fundamentals of thermodynamics. So we know applied thermodynamics is to understand the relationship of heat and work, and also how they transforms from one form to the other. So then firstly, because we know that we want to understand the relationship between heat and work and the energy transformation from one form to the other. So firstly, we need to have a look at what is energy. So in physics, in fact, energy is a quantity that provides the capacity to perform work or provides heat. And energy comes in many forms. The common forms of energy include kinetic energy. Okay? So for wind turbine, okay, we know for wind turbine, the function of wind turbine is capture the kinetic energy of wind, okay, to convert it to mechanical work. And finally, this rotational mechanical work is converted into electricity. And also we have potential energy. Okay, so this is hydrogen power. So it's the energy due to the position or the configuration of a system. Also, we have internal energy and chemical energy. So for the combustion of fossil fuels is to convert transforms the chemical energy to thermal energy. Okay, chemical energy is energy due to chemical composition. And sure, we have nuclear energy, and even Hong Kong. So we, when I think it's around 20–30% of electricity from nuclear energy from Daya Bay nuclear power plant. And we have electrical energy. So in order for energy to change from one form to the other, it must go through some sort of transition. So for this transition, how to achieve it is usually due to the change of the fluid properties. So for example, expansion, high pressure to low pressure. So for this change of properties of working fluid, there is expansion. This expansion can convert thermal energy into mechanical energy. And the transition process is a mechanism for converting one form of energy to another. So we have two conversion mechanisms like the work and heat. So let's have a quick look at the energy conformation. So for example, for a car, for an automobile, so we can see there are the following energy transformations. So first, the chemical energy in the fuel, okay, is converted into kinetic energy. Kinetic energy of the gas movement is the gas movement by combustion. Then the kinetic energy of expanding gas, okay, converted to the piston movement is the mechanical work, okay. Then the linear piston movement, okay, converted to rotary crankshaft movement. Then the rotational crankshaft movement pass into transition assembly and then through to drive the vehicles. So therefore, the rotary movement of drive wheels converted to linear motion of the vehicle. So we can see the energy transformation of combustion for automobile is here is the chemical energy installed in the fuels, and then through the combustion is converted into kinetic energy. This kinetic energy is the expanding, is the movement of the high pressure gas. So this high kinetic energy cause the linear piston movement, okay? Cause the movement of the piston. Then it's converted to the rotary crankshaft movement. Then finally, this rotary movement to drive the wheels. Then the rotary movement of driving wheels converted to linear motion of the vehicle. So then we can understand from this example the energy transformations. However, we always talk about heat and thermal energy. It is interesting to understand there are the limitations in the conversion of thermal energy. So low thermal energy we can consider as low quality energy. So what does it mean? It means, for example, that any conversions from other forms of energy to thermal energy is easy, okay, which can occur with 100% efficiency. Okay, other forms of energy to thermal energy is easy. However, thermal energy to other forms of energy is unique. Okay, it's very unique because it cannot be converted to other forms of energy. So it is very interesting, thermal energy. Any other forms of energy can be converted to thermal energy easily. So therefore, like the combustion, like for this example, fire is an example, and energy transformation is from the chemical potential energy of fuels into thermal energy. So this efficiency, if there's no loss, okay, energy losses, so this efficiency can be 100% efficiency. However, you cannot convert the thermal energy directly to chemical energy, like nowadays, like fuel cells, etc. So it's difficult for us to directly convert and easily convert thermal energy into chemical energy into electricity as well. So why? So because only a difference in the density of the thermal energy can be used to perform work, and the efficiency of this conformation will be much less than 100%. So later, even we know for power plants, the maximum possible efficiency is only 40%, 50%. So this is because thermal energy represents a disordered form of energy due to the temperature. So thermal energy is mainly due to, we can see, is due to the temperature difference. So then the measure of this disorder, in fact, is the entropy. So it's difficult to convert thermal energy to other forms of energy with high efficiency. Usually, the conversion efficiency is low. And to measure the disorder is called entropy. We will spend one lecture on to introduce entropy. So for a system, usually isolated system, usually the entropy will only increase. So, like for fossil fuels, in fact, is a chemical energy. So it is very interesting to understand thermal energy. And we understand that for this subject, we will mainly understand heat, work, and the relationship between heat and work. So we also know that heat or thermal energy is unique because for other forms to convert it, work to heat, okay? It's easy, and also the efficiency, conversion efficiency can be 100%. However, so the conversion from heat to work, okay, with a low efficiency. Heat to work, okay, with a low efficiency. So for this engineer thermodynamics, and also later we understand the properties of working fluid. Is also we know when the working fluid undergo the changes of properties. Usually for those processes, there's a change of energy. There is energy transformation. And here again about heat. In fact, heat is the form of energy which is transferred from one body to another at a lower temperature. So when there is temperature difference, there is a heat transfer. Okay, so the heat transfer always from the high temperature body to a low temperature body. So in the case of conduction, if there's direct contact, or convection, if there is a solid and a fluid surface, and also radiation. So heat is observed to be energy in transition. It is never contained with the intrinsic energy possessed by our body. So this is thermal energy. So for example, heat from the sun is the driving force of the most life on Earth. And firstly, you know, there is the solar energy will be converted into the our plant, so with as chemical energy. So for work, according to the definition, it is the product of a force and the distance moved in the direction of the force. For the thermodynamic work, we merely mention is the mechanical work. So in mechanics. So for example, so there's a work. There is a work input, work output due to the movement of the piston. Due to the movement of a piston, okay, there is a work input, work output. And also for a compressor, so we can see there's a movement of the piston. There's a movement of piston. So then there is mechanical work. If it's expansion, there's work output, and if it's compression, there's work input. Okay, we will stop here for 10 minutes break, so I can share with you. So for your questions, so raise your questions now and during the break. So we will come back after 10 minutes. Thank you. Okay, welcome back. Some of you asked me about the in-class quiz. In fact, there's only pass and fail, so you don't need to prepare for your in-class quiz. And also, you should attend it's scheduled as a tutorial session. So you have grouping. Okay, there's group 1, group 2. So for the tutorials, so during the tutorial session, you need to submit your answer scripts via the Blackboard. Okay, the second question is some of you ask me about what is intrinsic. So intrinsic means this is the energy you cannot see. Okay, how much heat you have. Okay, for example, I cannot see. Okay, I have how much heat. It's not I possess. Okay, I don't possess how much heat or how much work. Okay, it can be only energy in transition. Okay, so when there is a force, and in the force there is the body has a movement in the distance movement in the direction of the force. We can see there is work done. Okay, there is work done. So in the direction of the force. That means intrinsic. Okay, we cannot say. Okay, we cannot say. Okay, so for example, my phone. Okay, my phone. So how much energy my phone has, or how much work my phone have. Okay, so that is the meaning. So to understand. And so for this, the fundamentals of engineering thermodynamics, we know what is heat, what is work, and later we will try to find out the relationship between heat and work. Is magic, is very funny. And also we understand thermal energy is unique. because other energy forms of energy to thermal energy is easier, high efficiency. However, the conversion or transformation from thermal energy to other forms of energy is difficult. Not mentioned. Yeah, it's kind of difficult because the efficiency is low. And we also need to understand the properties of the working fluid, and in a system we always mention we mention system. So now let's have a look what is a system. So for engineering thermodynamics, we usually a system is defined. System we always mention for the system. You can see early we also have the term is like isolated system. Okay, so now let's have a look what is a system. So a system is defined as a collection of matter within the prescribed and identifiable boundaries. Okay, so for example, these are real boundary. Okay, for this piston, for this cylinder. Okay, for this cylinder, this piston. So we have inside, we have real boundaries, or we have real boundaries. So for this case, for this cylinder, we can see we have real boundaries. Okay, we have real boundary, and then we define that as a collection of matter. So inside there is a working fluid. Okay, there is some matter. The collection of the matter with these prescribed boundaries is called a system. And then accordingly, this is a system. We have a boundary, and outside the system, beyond the boundary, is called surrounding. Okay, so in the future, we always see, okay, between the system and the surrounding. So there is a there may be heat transfer, or there is change the movement. So this is a real surface boundary. Okay, this is real surface boundary. And however, for example, if we study a pump, this is for example, this is a pump. Okay, there's a flow in, and then is pumped out. Okay, pumped out. If we want to study the matter inside the fan, okay, beside this boundary, okay, here the crossing boundary, there is a there is also crossing boundary. This crossing boundary is imagined. Okay, so therefore, for the system, we have for a system we have its boundary. The boundary can be real surface. Okay, real surface. Okay, they can also be imaginary surface. Okay, these are imaginary surface, a boundary. So we can see this is imagined. And now look at when in the future, when we study any heat engines, for each component, when we work on it, we have to identify what is the system. So for the system, if there is a heat transfer, maybe there is a heat flow. Okay, there is a heat transfer from the surrounding into the system. Okay, maybe for the system is losing heat. Okay, is losing heat. Then we will see for the system it's very interesting is, so if there is a heat transferred into the system from surrounding, for the surrounding is losing heat, but for the system is gain heat. So therefore, we have to get the conventions. So we will mainly study, when we study the matter in the boundary, so we call it a system. For the system, this heat is heat gain, okay? But heat absorption. But for the surrounding, it's losing heat, is heat rejection. So that's therefore it's very important for us to firstly identify the system. For the system, we have to understand, for the system is a matter, is a collection of the matter in the uh, in the uh, in the system, in the boundary, and outside the system is called surrounding. Okay, is surrounding. There is an energy balance between the system and its surrounding. And also the boundary can be real. It can be also imaginary. So for example, with the crossing boundary, in fact, is an imaginary surface. And then also we observe that it's very interesting because for this one, we can see there is a real boundary, and for this one, we will find it's closed. So for the classification, we have for a system, we have a closed system, we have an open system. Now let's have a look. So how to classify, define if it's a closed system or open system? So we can see if it's it's depending on whether a fixed mass or a fixed volume in space is chosen for study. So for a closed system, for here, so we can see no mass transfer across the boundary. So therefore, we know that the mass is constant. The mass is constant. Okay, the matter mass is constant for closed system because there's no mass transfer across the boundary. It's closed. Then this system is closed. In the future, you will know because even for first law, second law, so we have we need to identify if it's closed system or open system. So when we study the energy equation for any system, we need to know if it's a closed system or open system. In fact, it's easy to understand. For open system, there is a transfer of our mass across the boundary. For example, there is a flow in, okay, then through flow out, okay. So it's open. There is a mass transfer, although this mass may be constant, may be variable. Okay, the mass can be constant. It can be also variable. So for this one, then is called open system. Okay, open system. This is its boundary. This is the system. This is boundary. This is a surrounding. So I think it's easy for us to know if it's a closed system or open system. But sometimes when for engineering problems, we will find it's still difficult to identify. Okay, some of you asked me about the laboratory reports. I think, in fact, I'm not responsible for the laboratory arrangement. So you need to approach Hilda Zhang, okay, for the detailed arrangement. So even for arrangement for grading, it's Hilda Zhang. She is responsible. So go to the course of BE2 laboratory. And as I have mentioned, even for example, there is a heat flow, okay? There's a heat flow into the system, okay? Because the surrounding is hot. Okay, so we can say for the system is heat absorption. So for this heat, for the system is heat absorption. However, for the surrounding is heat rejection. Okay, you can see for the system is achieve heat energy. Okay, however, for the surrounding it's losing heat. So therefore, we need the conventions. So for the conventions, we can see we will think all external inputs to a system is positive. Inputs to a system then is positive. For example, like we have introduced, is heat supply to a system is positive. If there's work input to a system, for example, so we compress it, then the work is positive. In other words, work done by the system is positive. Heat rejection by the system is negative. You have to always there's a agreement with the conventions, because if for the system and the surroundings, their values can be totally opposite. Okay, so be careful. Even for example, for like this is the system. Okay, any external inputs to a system is positive. Okay, like here, to a system is positive. It can be heat, is called heat absorption, and work input. However, if there's a work output, okay, then they are negative. Okay, the system do any work on its surrounding. For it is negative, but for the surrounding is positive. And sure, to understand the properties of the matter, we have to know there are some properties like we have learned before. So we have the pressure. Okay, so we know the pressure definition of pressure is defined as the limit of the force in the normal pressure on a unit area. And for the pressure, we understand it well. We understand there's one atmospheric pressure. Okay, so it's very useful to understand its units. So for the standard one is so for the standard one, in fact, the units is the normal pressure on a unit area. In fact, this is the standard units, is Newton per square meter. And this is also equal to Pascal, okay, 1 Pa. However, pressure units of Pascal is a very small unit, so we are using a kilopascal or bar to to describe the pressure, so in our engineering practice. So for pressure, we also have to understand if there's a relative pressure or absolute pressure. Let me see if we have it. Okay, no. Okay, relative pressure. So for absolute pressure is totally here is totally here absolute pressure. However, usually we are using the atmospheric relative pressure. Okay, because we want to know the difference between the actual pressure and the atmospheric pressure. We want to know the space is a vacuum or with a positive pressure. Okay, so therefore we understand that usually when we mention sometimes the pressure, so we are mention is the relative pressure, and also for our gauge, for our equipment to measure the pressure. Usually the reading is a relative pressure, because this is the reading is the difference between the absolute pressure and the atmospheric pressure. If the pressure, absolute pressure, is smaller than the atmospheric pressure, then we call it vacuum. Okay, vacuum pressure. Vacuum pressure is vacuum. So that means the pressure is smaller than the atmospheric pressure. So look at here. So usually the useful units conversions is useful is kilopascal or bar. So 1 bar is equal, so 5 zeros Pascal. Okay, and also the other very useful one is atmospheric pressure. 1 atmospheric pressure is equal to 101,325 Pascal. So be careful, 1 atmospheric pressure is not too equal to 1 bar. Okay. Bar is not equal to 1 atmospheric pressure. And also for the measurement, we are using manometer, and also the gauge. Okay, the pressure gauge. The pressure gauge. You can see the pressure gauge. The reading, the reading, in fact, is the relative pressure between the actual pressure and the atmospheric pressure. So therefore, its reading is relative pressure. The reading is relative pressure. Even for the manometer, so we can see the difference. When we measure the pressure, so here, the system pressure, so you can see the reading. In fact, this is usually open to the air, is air. So the pressure difference between atmospheric and the system matter. Okay, so now we understand usually when we mention pressure is relative pressure, because the reading from our measurement equipment, the reading usually they are relative pressure. Okay. And temperature. So for temperature is a property we can use to distinguish the hot bodies from cold bodies. So what we need to be careful is also the conversions and the units of temperature. So for us, usually we mention degrees Celsius, like our body temperature is 34.5 degrees Celsius. So nowadays, every time we measure our body temperature. However, from the United States, they are usually using the Fahrenheit degree. Okay, this one. But most important, for engineering thermodynamics, most equations we are using Kelvin scale. Okay, so this is for this subject. For engineering thermodynamics, most equations, even like a perfect gas equation, we have to use Kelvin scale. So we have to remember the conversions between Kelvin scale and Celsius scale. Okay, so we consider we have to minus for to plus 273.15. Even for radiation heat transfer, we have to use the Kelvin scale of temperature. And also for engineering thermodynamics, most equations we have to use the absolute, the Kelvin scale temperature. So the temperature, in fact, is related to the average kinetic energy of its atoms as they move. So it's we can see we can use it to distinguish hot bodies from cold bodies. And how to measure the temperatures? In fact, we have the very conventional one, thermostat to liquid in glass thermometer to measure our body temperature and our air temperature, indoor, outdoor temperature. So however, for engineering, for our engineering practice, we are usually using thermocouple to measure the temperatures of water, of air, etc. We are using thermocouples. So a thermocouple is a junction between two different metals that produces a voltage related to temperature difference. Okay, and there is a so this touch the target surface, then we can measure its temperature. And what is good is the digital fingers can be plugged into a multimeter with a direct display. And also, in fact, we can also connect it to a data logger for long time real time temperature monitoring. Sure, you see our main campus, we also have thermal. Okay, there is also thermal imaging camera, so we can sense using we get the full picture of the measured body by using the thermal imaging camera. I have one in my laboratory. So you can measure the temperature distribution of our body. And besides pressure and temperature, we also need to understand for the matter. So what about their states and other properties? Now let's have a look at the property, state, and processes. So for the okay,
Bye.